This is Doug Nemeth of the U.S. Fish and Wildlife Service's Idaho Fish and Wildlife Conservation Office. I'm going to speak about a two-phase survey methodology for western pearl shell mussels in clear water streams and include some notes on mussel behavior. The Idaho Mussel Investigations Project is a recurring, dedicated effort with 4 objectives. Objective 1 is to document mussel species and their locations throughout Idaho in its 4 ecological sections. Objective 2 is to determine and monitor distribution, abundance, and demographics of freshwater mussels in Idaho. Objective 3 is to develop methods for estimating the distribution and abundance of mussels, and Objective 4 is to support mussel translocation efforts. Today I'm going to talk about Objectives 2 and 3 primarily, and those are to determine the distribution, abundance, and demographics of mussels and to develop methods for estimating mussel distribution and abundance. Please note that during this talk, when I say mussels, I'm specifically referring to western pearl shell mussels. The outline for the presentation are Phase 1 surveys. I'm going to talk about our Phase 1 surveys, which provide broad spatial coverage. They're an index of relative abundance. And then I'm going to talk about the sources of Phase 1 variation. Next, I'll talk about how do Phase 1 abundance estimates relate to actual abundance from Phase 2 quantitative surveys. And then I'm going to talk about some mussel behavior and factors that can affect abundance estimates with some other notes. The issue is that much of Idaho is unsurveyed for native freshwater mussels. There are few to no long-term monitoring sites, and you need to know what you have, mussel species, numbers, and locations, before you can implement a monitoring plan. So the need was to develop a fast, replicable method to provide mussel distribution, mussel species composition, and abundance information. We wanted it to be simple, replicable, and provide broad spatial coverage, which is to say it could be conducted quickly, and we wanted results to be comparable across watersheds. The requirements for our Phase 1 surveys were to provide information on mussel distribution and an index of abundance to inform future quantitative long-term monitoring and other needs. We wanted more than observe, not observe, or as some people say, presence, absence. It had to be quick to conduct, broad spatial coverage, minimal training, it was simple, it was replicable, anyone can do it, and it was applicable to wadable, clear water streams with excellent visibility. Most of the streams that we worked in developing this methodology were stream order 3 and 4, occasionally a stream order 5 or a stream order 2, but for the most part, stream orders 3 and 4. How did we conduct our Phase 1 surveys? We used a clear bottom view bucket, and we walked the stream where we felt mussels were most likely to be found, and we counted them. This method was adopted from Cosgrove et al., where they walked 160 rivers in Scotland and surveyed for mussels. We surveyed an approximate 1 meter wide swath through a given reach. It took us 10 to 15 minutes per 100 meter reach, which is to say it was relatively quick, and we ended up with an index of relative mussel abundance. It's important to note that we intentionally and willingly sacrificed accuracy for broad spatial coverage. The question we were asking was, are there 100 mussels present or 500 versus are there 100 mussels present or 125? This is an example of what a Phase 1 survey output can provide you. In 2019, each surveyor walked about 10 100-meter reaches per day, a kilometer, which is to say that it met our requirement for being quick. We surveyed 35 streams at 59 distinct locations, 130 kilometers surveyed. We saw just under 180,000 western pearl shells, and we found 2 species of mussels, western pearl shells and floaters. This is another example of an output. This is what we call our heat map, which shows the relative abundance and distribution of western pearl shell mussels in 70 contiguous kilometers of the Lolo Creek watershed. Now, this kind of information, distribution and abundance, can be very helpful for habitat protection decisions, whether or not you're going to allow, say, mining or logging or a bridge crossing, also with long-term monitoring planning for mussels and additional studies. Here's a zoom in on that figure so you can get a better idea of the type of density information that our Phase 1 surveys provided. You can see that we had some very high density areas, which greater than 1,500 mussels per 100 meters squared, and some areas that had 0. So this provided relative abundance at a smaller watershed scale. Here's another example of an output, relative abundance at a larger spatial scale. And this is the northern half of Idaho, different basins that we surveyed. And you can see that we're able to say that, we had varying densities of mussels in different basins. Now, it's important to note that we're not making implications for the basin overall, but for the stream reaches we surveyed, we can say that yes, some reaches had very high mussel densities and some had very low. So, in summary, Phase 1 surveys provided mussel distribution and abundance across both small and large spatial scales. This kind of information can inform localized actions such as habitat protection, can provide regional insights into mussel occurrence in some watersheds but not others, different abundances, species compositions, and inform choices for long-term mussel monitoring. And that's certainly how we're going to use our Phase 1 surveys to help install some long-term monitoring sites. Phase 1 survey variability. Please don't try to decipher this image. This is an image of our Phase 1 survey data sheet, and I'm showing it only to bring up some of the variables that we record, which include the distribution pattern. Please note the distribution pattern. We have 3 of those, and we're going to talk more about those. The substrate, dominant substrate, a gradient, and the stream width. This slide shows Phase 1 survey variability by stream width and mussel distribution pattern within the reach. You can see very easily that variation increased with increasing stream width, particularly once we got a width greater than or equal to 11 meters. The mussel distribution pattern within the reach also affected variability. The continuous distribution, the red dots, were the least variable. Discrete beds, which is a patchy distribution, had the greatest variability, and they are shown as the green triangles. And random distribution also showed increased variability, but primarily at greater stream widths. This slide shows Phase 1 variability by the number of mussels counted. On the y-axis we have the coefficient of variation. On the x-axis we have the mean mussel count going out beyond 4,000 mussels. The red dots are reaches with a width of less than 11 meters. The blue triangles are reaches with a width of greater than 10 meters. And what you'll see is once the width gets larger than 10 meters, you have high variability regardless of mussel abundance. It's probably prudent with a width of greater than 10 meters to use a second surveyor, and some people have done this, although we haven't evaluated it. When the stream width was less than 11 meters, there was consistent lower variability regardless of the abundance of mussels. This slide shows Phase 1 mussel counts for 3 different fixed sites, blue, orange, and gray, visited in June, July, and August. You can see that the error bars for any given site overlap, indicating there was not a statistically significant difference. However, you can also see that the point counts decrease with each successive month, indicating that the time of year can affect the count. Also, anecdotal observations over the years also indicated that maximum abundance on the surface may occur in June, and we suspect that this may be related to reproduction. This slide shows Phase 1 survey variability by surveyor. We had 6 surveyors. They surveyed a different number of fixed sites, the amount of time each surveyor took, the percent of the counts that were higher than the mean, and the average percent of the mean. And what you'll see here is that surveyors 4, 5, and 2 were within 2 to 4% of the mean count on average. Surveyor 1 consistently produced counts higher than the mean 80% of the time, but was still within 6% of the mean on average. Surveyor 3 was 16% greater than the mean, whereas Surveyor 6 was 15% less than the mean. So the counts are kind of bouncing around here, and this is why it's important that new surveyors are calibrated with the team by conducting phase 1 counts on the same reaches, and preferably you want to use reaches of different densities and then compare your counts. Phase 1 survey accuracy. Hypothetically, if a phase 1 survey indicated a relative abundance of 100 mussels in stream reach 3 and 500 mussels in stream reach 4, are there really more mussels in stream reach 4? And we answered this question by using a phase 2 quantitative survey. Phase 2 surveys are quantitative abundance estimates. Phase 1 surveys are an index. Phase 2 surveys are intended to be an accurate estimate with associated error. Our immediate need was to validate phase 1 information. We asked the question, how does relative abundance information from a phase 1 survey relate to actual abundance estimated from a phase 2 quantitative survey? The diagram on the right here shows a hypothetical schematic of belt transects for a phase 2 survey. We used belt transects where we surveyed from bank to bank, perpendicular to the stream flow. We used systematic sampling with 3 random starts, which allowed for an unbiased error estimate. This was from Pooler and Smith. We used multiple random starts, and that created actually very little extra work, but at the same time gave us the error estimate that we could calculate confidence intervals with. We used 0.25 meter squared quadrats, which was also from Pooler and Smith, 2005, and we excavated every third quadrat. We're going to talk a little bit more about excavation. Excavation is in Smith et al. 99 if you're interested in that. This is a picture of snorkelers doing our phase 2 quantitative surveys. We have 1 to 2 snorkelers. We prefer to use 2. We have 1 data recorder. If you're going to take mussel lengths and tag mussels, you're going to want 2 additional people. When we built our quads, we built 2.25 meter squared quads, built them together. We found that that was a little easier to stay on track as we moved across the stream. We surveyed 12% of the stream bed area, 4% for each random start, and we excavated every third quad and measured mussel length by the mussels that were recovered on the surface and those that were buried. Generally, it took us 1 day to do a 100-meter reach with phase 2 surveys. All right, so how accurate are the phase 1 surveys? Now we're talking about phase 1 surveys that were conducted in streams with less than a 10-meter width. And what you'll see is that we've got a pretty good relationship. We have an R squared here of about 0.86. R squared was influenced by the very high abundance point that we have there, that's over 4,500 mussels. You'll see that the relationship was less predictive at lower phase 1 abundances. Now this is a regression rather than abundance, but with absolute density. And the relationship between phase 1 and phase 2 abundance gets stronger when measured by density, and that's because density incorporates the stream width, which we've already learned affects the estimate. And you can see that we've got an R squared here of 0.95. So this is the same graph, but what we did here is we truncated the x-axis. It no longer goes out to over 4,000, but it stops now at 1,600. And you'll see the relationship between the phase 1 and phase 2 densities is less, but it's still strong. We truncated the x-axis because any reach with over 1,500 mussels is going to be categorized as a high abundance, so there's really no need for us to count. Once we hit 1,500, we just stop counting. It's a high abundance reach, and it's just noted that way. It's interesting, though, you can see how the low, medium, and high density sites do cluster, however, together. This slide shows point estimates from quantitative Phase 2 surveys with their associated Phase 1 counts. To recap, we surveyed 12% of the stream bed for the Phase 2 surveys with 3 random starts. You can see that the confidence intervals were tight for some estimates and looser for others, regardless of abundance. The broader confidence intervals were related to a patchy distribution of mussels in the reach. The percent of mussels buried ranged from 8 to 45%, and we're going to talk a little bit more about buried mussels later. In summary, Phase 1 surveys provided quick, replicable, and simple method that provided results comparable across watersheds. Phase 1 surveys provided species, distribution, and abundance information across watersheds, basins, and statewide scales. Phase 1 survey abundance data were affected by stream width, mussel aggregation type, month, and surveyor. Phase 2 quantitative surveys demonstrated that Phase 1 surveys were sufficiently accurate to inform relative mussel abundance and densities, at least categorically, low, medium, and high abundance density. Phase 2 quantitative surveys, as applied with a systematic random design with 3 random starts, provided abundance estimates with confidence intervals. And the surveys as constructed also sampled recruits and took 1 day to complete a 100-meter reach, less than 11 meters wide, with 3 people. I'm going to switch gears now and talk about some mussel behaviors that affect mussel survey results and some other notes that we found interesting. I'm going to talk about temperature, gradient, substrate size, the proportion of mussels on the surface and buried, mussel translocation, multiple handling of mussels, and detecting pit-tagged mussels. Water temperature can have a large influence on the number of mussels that you see on the surface. Here in Idaho, we have anchor ice in the streams that occur over the winter, so the mussels have to bury to get away from the ice. This graph is from the springtime when we began looking for mussels, and at 4 centigrade we were looking in a reach where we knew there were mussels, but we just didn't see any. By 7 centigrade, all of a sudden we started to see some mussels, and by 11 centigrade we started to see a lot of mussels. So the proportion of mussels on the surface can be heavily regulated by water temperature. Stream gradient also strongly influences where mussels can occur, and you can see that in low gradient reaches by far had the highest density of mussels. Mussels can occur in any gradient, but if it's going to be a high gradient reach, they're going to be behind boulders or log jams or something that provides protection from high water. Substrate size. There's clear preference for some substrate size over others. They can occur in any substrate size, but clearly where we did our work, coarse gravel, fine gravel, and cobble were definitely preferred areas. This is an image of one of our high density mussel sites. You can see that there's a lot of fairly good size cobble present, as well as large gravel, smaller gravel, and sand. This slide shows a table from a series of sites where we looked at mussel proportions on the surface versus buried by substrate type. And what you'll see here is that in sandy substrate, we had a lot more mussels on the surface than we did in cobble and gravel. Cobble and gravel, most of the mussels were buried. Also note, we have different length ranges for surface and buried mussels. Surface versus buried. Smaller, younger recruits tend to be buried, and you can see that very clearly here. We've got the buried mussels are the red bars, and you can definitely see that the smaller ones tend to be buried, whereas the surface mussels tend to be larger mussels. This is something that was very clear in our watershed where we've been developing these methods. However, talking to other people in other basins, this may not be the case. Mussel translocation. This table shows some interesting information. The data in this table was collected from some test plots that we established within an area where mussels were being removed. The stream channel is going to be dewatered, the mussels are going to be moved, so we set up some test plots and we removed mussels from the surface in June and we measured them. We dug down as deep as we could in those same test plots and recovered buried mussels, and we measured them. And in June, the length of the mussels on the surface was 53 millimeters, and those that were buried was 45 millimeters. We felt pretty good that we had gotten most of the mussels from these areas. Now, these were relatively small areas. We could get an accurate count. We were feeling pretty good that we got them all. We went back 20 days later, and we had more mussels. But what was especially interesting was that the mussels on the surface now averaged 44 millimeters, which was similar to the average mean size of the buried mussels in June. And the buried mussels 20 days later in July averaged 33 millimeters. So the translocation of all mussel age classes probably is going to require multiple visits. If you're going to do an effective job at translocation and you want to move the entire population, which means different age classes, which you probably want to do, you probably are going to need to go back to that site more than once. This slide shows the effect of multiple handlings on the proportion of mussels on the surface within a given mussel aggregation. On the y-axis it says the proportion of initial number of mussels observed. So when we initially started out, that would be number 1. This is where we started. This was the total number of mussels. With subsequent dates, as we handled the mussels, the red squares and the blue triangles show aggregations where we handled them, and you can see that the number of mussels declines with time. Over here by October, the water was getting cold, winter was coming on, so the mussels were going to bury anyway. But as we handled the mussels, the proportion on the top decreased. We also had a never handled control unit, which are these black circles. And we never touched these mussels, and this photo here shows those never handled mussels. We had these pavers put in place so that that quadrat could be dropped in exactly the same place every time. We put that quadrat down with minimal disturbance to the substrate, and these mussels were never touched. And what you can see is that the proportion of mussels on the surface really didn't change until the water really got cold in October, and then they buried. But we didn't handle these mussels, they stayed on top. We handled these mussels and they disappeared from the top. Detecting pit-tagged mussels. Tagging mussels is important for collecting demographic data. If you're going to pit tag mussels, be prepared for pit tag litter. We had mussels tagged in 3 different locations, a total of 90 tags out there. And the first time we went out to find the mussels, we got 90 hits on our pit tag scanner, and we were feeling pretty good about that. And we went back to the office, and what we learned was that more than half of the pit tags that we found were actually pit tag litter from anadromous fish. The watershed that we're working in has been is full of Chinook, steelhead, and coho, and they've been pit tagged in there for over 20 years. Detecting pit tagged mussels is much harder than we expected. we believe that the issue is that mussels do move, and the orientation of the pit tag on the mussel as it moves changes, and as that orientation moves, our ability to detect it might increase or decrease. And what we would see is that we would go to a location, and we might get, the first 3 times we went out, we see the same mussels, and then all of a sudden we'll go out on a different occasion, and we get 3 or 4 mussels that we've never seen before, and it's like, well, where were those at? And then we go back the next time and we don't see those again, but we see different ones. And so it's difficult to recapture these pit tag mussels, and so one of the mitigative measures that we use now is that when we pit tag mussels, we put them in a fairly small localized area. We mark it with our sub-meter GPS, so that we know we're getting back to the same area, and we believe that this is going to maximize our ability to recapture mussels. So in summary about some of these behaviors and other notes, water temperature definitely affects the percentage of mussels on the surface. Higher mussel densities occurred in lower gradient reaches. Mussels can occur in all substrate sizes, and the percent buried can be dependent on substrate size. Smaller, younger recruits may be buried. Effective translocation of the entire population, all ages, may require multiple translocations and or excavation. And mussels may move after handling. Detecting pit tag mussels may require multiple visits due to changes in mussel orientation. And clustering pit tag mussels in a small area might maximize your ability to detect them in the future. The summary of the summaries then. Phase 1 surveys provided a quick, replicable, and simple method that provided results comparable across watersheds. Phase 1 surveys provided species distribution and abundance information across watersheds, basins, and statewide scales. Phase 1 survey abundance data were affected by stream width, mussel aggregation type, month, and surveyor. Phase 2 surveys demonstrated that Phase 1 surveys were sufficiently accurate to inform relative mussel abundance and densities, at least categorically. And Phase 2 surveys with 3 random starts provided reasonably accurate abundance estimates. Parameters affecting mussel detectability on the surface include water temperature, stream gradient, and substrate size. Smaller, younger recruits may be buried. Effective translocation, all ages of the population, may require multiple translocation visits. And detecting pit tag mussels may also require multiple visits due to changes in mussel orientation. The end. Thank you.